because today is a little heavy on theory. Are you guys game to moving forward, or you feel that you would rather just review what you have done?
What are you trying to cover after
Now
this?
is a big topic. It is the back propagation. Okay, let me introduce it. I won't do it fully. Let me just sort of introduce the topic and we'll do it a little bit. So imagine a neural network. And I'll today do it without mathematics, and next time I'll do it with mathematics. How about that? Because I think today, this late, your minds may not be fresh for mathematics. So imagine a neural network. Huh? There is a layer 1, and this is the input, x1, x. Let's say p-dimensional input is going to all of them, and so forth. Going to each of these. What are these things called? What are these circles called inside each layer? Neurons, right? So neurons. So it is there, and then that goes to layer 2, which will have God knows how many layers, how many neurons of its own. I'll just make it 4 of these, right? Or 5 of these, let's say. And then so it keeps going on, and you come to a layer, a final layer. Let's say that you have layer L minus 1, and the final layer is layer L, right? So this kind of a thing, and it produces the output. Y hat comes out of it, right? So when you give it the X vector, some vector with some data point, so I had some data instance, and I won't put the subscript because it gets to be quite noisy with lots of subscripts. So assume that you have given one data vector X, and out comes a prediction, because this will keep going down. So what happens? You give it X, there'll be weights here. It will go through an activation here. Remember the basic idea? Each neuron is made up of what? An activation function, a distortion function, which I write it as sigma, but it could be a Z. Then their weights W, right? And W's, and then whatever input comes, x1, x2, x3, let's say, and if you were to write it, you would say Z is equal to, and there is a bias term, B, bias plus W1, x1 plus W2, x2, plus, let's say W3, x3, in the case of this, to produce the result Y hat. In the case of a single neuron, this is how you would think about it. You would say, first of all, compute Z. And once you compute Z, give me a moment, guys. I'm a bit tired standing. So I'll sit down. I'm lowering my table. A little bit more. I will lower it. Okay, this is good enough. So you can write it like this. Now you realize that in a single neuron, the Y hat is the activation of Z, isn't it? This is the relationship for a single neuron. That example neuron. But now, when you create a complex neural network, things become very interesting. Let's say that this entire neural network, you gave it X, it produced Y hat, but it turns out that the value was Y. And so Y hat is, let us say, much bigger than Y. Y hat has overshot the real value of Y, right? So how much would be the error? Error would be Y hat minus Y. And of course, I'm not summing over all the data points, etc. Just for notation, I'm keeping it simple. And so your loss would be, let's say if you square the error, Y hat minus Y square, let's say. for simplicity's sake. Of course, there is a summation symbol to sum over all data points, etc. Once again, as I said, I'm going to gloss over it for the time being. But now you say, well, my loss was too much because y had short y. So how do I decrease it? How do I decrease my loss? Because this is what you're trying to do. So you can say, well, that is very easy. Let's draw the diagram. Let us look at the final layer. And now let's bring in our subscripts. Let's say that there is a neuron here, right? Let's call it jth neuron in the layer this. Then we can say, and let's say that this is producing an activation A of J, right? Activation J. Now you can say that, and let us say that, all the other neurons are also producing their activation, and you are looking at the somehow, and this is not realistic, but I'm deliberately creating a loss function because there are many of these J's here, sum squared. So what happens is that the Y that you get, it is made up of, it's a vector, and you expect this to be, let us say 0, 1, 0, 0, 0, something like that, right? It's a vector. So, but what you produced is you produced light bulbs lighting up to produce certain values. Now, in the language of machine neural networks, people often call it as the energies, what the output layer produces sometimes are called the energies, right? Or the potentials or something like that. People use physical intuition, but whatever it is. And let's say that you do this. Now, what would you like? Let us say that you produced, let's look at this value, right? You have neurons and something is burning very bright. It produces a massive activation. AJ is bigger than the other activations. To the extent that these things are being fit here, this is nothing but what is Y hat? It is the activation J, the prediction J, activation minus YJ square, right? This is what the prediction comes out from this node. It's burning bright and you have overshot. So what does it mean? First of all, if this is big value and these are close to 0, let's say that these are 0.01, but this is 0.9. What does it mean? This is contributing a lot to the loss, right? And you are better off making changes to this guy than small changes to this guy, to something that's practically a bulb that's not burning at all, isn't it? But that is what it means. So you want to, if you want to really fix your loss, you are better off making some small change to this activation. But how do you do that? That's the problem, right? So I will solve this problem first for one neuron. Remember, going back to the picture of one neuron, and we'll develop the idea of back propagation is equal to the activation. This is also called the in the new language, we'll call it the activation from this neuron. We will say activation is equal to sigmoid of Z. Now, what is Z? Z is W1, W2, so W1, W2, etc. And the inputs that are going into it, X1, X2, etc. So this is a bias term, bias plus W1, X1 plus W2. Let's keep it in 2 dimensions, this. And your loss is equal to Y hat minus Y square, which is the same as activation minus, which is activation is this, minus Y. Y is being the reality square, which is the same as like basically sigma Z minus Y square. That is why you see that if you want to make a change in this, what do you want? you want to, the loss is very sensitive. Let's look at the derivative of this with respect to A. If you look at this, sigma, what do you get? You get 2 sigma z minus y. Does this look right? This is basic calculus. Now, think about it a little bit. What it is saying, so now let's interpret it. And there's a very nice way to interpret it. It says that if you change this A, actually, let me use the word activation. If you change the activation a little bit, how much impact it will have to the loss? In other words, if activation A goes through a minor perturbation, or think of it as wiggle, you wiggle it, you change it by, and this is very sort of a notation, a tiny amount, then how much did the L change? That is delta L, right? How much did it change? Right? So for a tiny wiggle of A, if the change is loss changes quite a bit. If this is quite a bit, what does it mean? L, if, so that is W, what that is WL, WA, right? How much did small change of A cause a change of L, roughly speaking? This is a hand-waving argument. And so gradient or derivative or derivatives measure sensitivity. That's one intuition you can carry. Sensitivity to input. Here input being sensitivity to the denominator or whatever. Sensitivity. If you make small changes here, how much does it change? So the bigger this value, the bigger the gradient, the more it changes. The more it changes. See, the intuition is very simple. Imagine our y and x. If y and x are like this, x, at this point, a unit change in x, delta x, causes this much change in delta y. Whereas here, the same unit change in x does not cause the y to change much, isn't it? So you say here the gradient or slope is high, here the slope is low, right? That's what it is. Slopes measure sensitivity of the response. How sensitive is the response to the input? That's one way to look at it, right? But now, if you were to do that, you ask this question: when I do gradient descent, what will happen? I can't change activation. Activation is not in itself something that you can change. What you can change in this neuron are the W's and the bias terms, isn't it? If you want to make a different model, you have to change the parameters. So the way to think about it is to say, and this is the part, pay attention. You say that if I change the W a little bit, what I really want to know is this, because the gradient descent step says this. And so what I'm really looking for is to compute this, isn't it? How much does the loss change when I change the weight, any one of the weight a little bit, right? And of course, I've reduced the subscript. Maybe I'll just put the subscript back, WI. Right? Likewise, the bias is for the WI tilde is equal to bias I, bias tilde also tilde is equal to a bias minus alpha to the bias term, right? This also is true. So now let's figure that out. Let's make a, if I make a, let's go back to the picture of a neuron. I'll reproduce it here, W1, W2, X1, X2. And let's see if we get this intuition right. And this is the activation, the distortion function to produce Y hat is equal to A the Z, which is A is equal to, well, I'm calling it activation and Y hat interchangeably. This is the sigmoid of Z. So let's do one thing. Let's see if I want to see the sensitivity of the loss to W. Let's change the W a little bit. Any one of the W, WI. If it changes, well, if I change this, what will get affected? Z will get affected because Z is B plus WI XI, right? Summation of W1 X1 plus W2 X2. This is what it was, right? So if I change any one of them, 1 or 2, this will change what? It will change Z, right? Because the inputs are constant. Input you can't play with. If you wiggle around the W's, it will end up wiggling around the Z, all right? So let's write that down. So this will get changed. Z will get changed. But if Z changes, if this changes, what change will it cause? So let me make a causal change. Change in this, let's take the 1. Let's be very explicit. W1. If I change W1, Z will change, right? So the causal relationship goes like this. This will affect this. Does that make sense, guys? If you change W1, it will have an impact on Z, right? Because of this formula, because Z by definition is this. But if you change Z, what will get affected? If you change Z, what will get affected is the activation, this A. A is nothing but activation of Z. So A will get affected, isn't it? So this affects this. This affects the activation function or the output, isn't it? So far, so good, guys. And what does change of A affect? Well, A is the output. If you change this, your loss will get affected, isn't it? Your net loss will get affected. So you can say this part now, change in A causes a change of the loss function itself. And therefore, a small change in W1 caused a change in Z, change in Z caused a change in A, change in A caused a change in the loss function. And so changing W affected the loss function totally. And so you say this is W1 is equal to this. So far, so good, guys, for this one neuron. And let's generalize it now and write it as Wi, some ith W for that neuron is equal to dz dwi, because it could be 1, it could be 2. The argument would still be the same. dA activation dz dl, the gradient with respect to the activation function. And this is a more general result, right? Likewise, you could have said the same thing with respect to B is equal to dz dB dA dz dL dA. So this is called the chain rule. What we just did is in calculus, you call it the chain rule, that how does the impact propagate? All right. You must have used the chain rule in your high school at some point while doing calculus, but this is a result. Today, what I will do is not go any further beyond one neuron. We won't go to the full neural network because that will take more time. I can see tiredness now. But what I will do is I will present you the chain rule using a different intuition, right? Let me do this. And I will bring that intuition forward using a sort of a joke. There is a TV serial, a TV show for kids, very popular in the US. It's called Psych. Anyone has known that? Psych. is for, well, it's for teenagers, it's for young people, children, like typically the age groups between 6 to 13, 14 like it very much in the US. So my children used to like it very much. And one day I was sitting through and listening to watching it. And one of the episodes had, and there are two characters. One is a very rational and sensible person named Gus. And one is a crazy genius, but not terribly well educated or this thing. His name is Sean. So they obviously, it's a mystery. They go solving mysteries, often murder mysteries and so forth. So think of it as Hardy Boys or Enid Blyton or something like that. So at one point, Sean, they decide that they need to they need to run for the mayor's position in the city to solve a murder. So when they do that, Sean has to give a speech and he has to have a meeting with the press. So Gus gives him a very good piece of advice. He says that, see, if you are a politician and a journalist asks you a question, you don't have to worry at all. Don't answer that question you don't want to answer. Answer instead a question that you want to answer. A somewhat similar question adjacent to it, and answer it confidently and you'll be fine. And apparently there's a lot of truth to it, because if you ask a politician a question, you always see that they're answering a slightly different question, the one that they want to answer. And the purpose of a good journalist is, of course, to continuously bring the person back and force them to answer the question they do want to ask, right? So it's somewhat like that. Chain rule, I often think that in calculus is like that. So I'll take an example and try and make it real. I just cooked up some weird problem. So suppose you have a function that is y, let's say y of x is equal to sine of e to the minus cosine x square. You realize, and I say find dy or dx. Now, this hopefully looks scary enough to you, but I'll give you a little table that will help you solve this problem. All that you know is that if you take x to the power n, its derivative is n x n minus 1. If you take the derivative of e to the x ax, its derivative is a e to the power ax, simple. And if you are given a sine, its derivative is cosine x. If you're given cosine x, its derivative is minus sine x. This is all you know, right? And the thing is, you're supposed to find this derivative and you say, oh gosh, this is hard. So let's try to solve the problem that we would rather wish we had, and see, chip away at this complicated problem and see if we can solve it. So what we will do is, first we'll pretend that this entire thing is some other variable called w, right? And we will write y is equal to sine w. If we write it like this, can we find dy dw? What would that be?
Cos W.
Cosine w, isn't it? But that is not what you were looking for. You were supposed to find dy dx. So, well, some partial credit. Let's move forward. But w now is a smaller problem. W is equal to e to the minus cosine x square. Oh boy, that looks scary. If only this part was some other variable, let me just call it p. So suppose w could be written as e to the minus p. Then if it is so, then can we do dw dp? What is that?
Minus e to the e power minus p.
To the minus p. Well, that looks like an improvement. But then, and so now we can put these two together, multiply these two together, and we came up with dy dp. But then p is equal to cosine x square. That still looks hard. We can't solve it using a table. So let's make this inner part as q. And so we can write this p is equal to cosine q. Now can we find dp dq?
minus sine q.
Minus sine q. Oh, and what is q is equal to x
X
squared.
square.
So can we find dq dx
2x.
to 2x? This now this thing is beginning to sink, because now I can say what happens if I do this: dy dw times dw dp dp dq dq dx. I know that small change of x causes q to change, small change in q causes p to change, small change in p causes w to change, small change in w causes y to change, and therefore small change in x causes y to change. And so this is dy in response to small change in x. And I've just found that. And we can start plugging in values now. We can say cosine w and minus e to the minus p, right? And times minus sine q times 2x. And now let's start resolving it. First of all, we can get rid of these two minus signs. And so we will end up with this. We can solve this by saying 2x. Now, what is w? W, we realize, was this thing, right? So let's do that. 2x cosine e to the minus cosine x squared. Wow, pretty complicated thing we did. E to the minus p. Now, what is p? P is cosine x squared. Then so we can write cosine x squared times sine q. What is q? So we have sine x squared, and lo and behold, we solve this problem. So we say dy dx is equal to this. And you realize that we solved it by simply looking at this simple table of derivatives, isn't it? And applying what is called and what we did is we broke the problem down successively into smaller and smaller problems, isn't it? We chipped away at the problem. Right? And so this is the way you can use the chain rule to solve complex problems. Now, so at each
As if
stage,
I think it's e power minus cos x square.
I missed e to the power somewhere, right? W,
Yeah.
where is it? Cosine W is this.
After cosine, e
After
power
cos-
minus.
right, e to the minus. So this is even more complex. You're right. E to the minus p, e to the minus cosine x square. But see what a complicated derivative we solved. And we solved this complicated derivative. Thanks for correcting me here. We solved this very complicated derivative by just chipping away at the problem slowly. And now I will, today we are almost getting over time. It's a complicated thing. So what happens is that there is a final layer producing y hat from the responses here. And from the y hat, you get the loss. The loss is response to the activations, which is the y hat is the activations from the last layer. These activations are affected by inputs from the previous layer, not only by the weights, but the inputs from the layer -1, right? This is the layer L. And those inputs are affected by layers before that to before that, and finally to the input, the actual X. So do you see the relationship between the complicated problem we solved and what we are going to do? Right. What we have to do is we have to find the loss. So what does the loss depend upon? Let's see. At the last layer, the activation depends upon a bias. So suppose you take any one node here. Let me call it the ith or the jth node. This jth node contains some weights coming in. Let us say that, let's look at this weight coming from the ith, this one. So W, actually, the way you do it is the opposite, I and J. And so this notation, by the way, you'll find counterintuitive. You put the target first and then the source. Wij is the connection here. But what is this node producing? It's producing its own activation, AJ, coming from the layer L minus 1, and this is the layer L. So now we are throwing in all sorts of subscripts and superscripts here. This is it. This belongs to the layer L, right? And this also has some bias terms, Bi of the layer L, right? Bi of the layer L. So now you realize that this is producing its activation. Activation of the ith node in the layer L is equal to the sigmoid of whatever Z is here, sigmoid of Zi, sigmoid of Z, I mean, not sigmoid, activation of Zi, it need not be sigmoid, is equal to a bias I plus, what is it? It is all of these Wi, J, A, J, summed over all possible values of J, like different nodes that are feeding into it, right? So I will, whenever you see some subscripts repeated, assume that you're summing over all possible values, right? This is the so-called Einstein's summation notation, so that you don't keep putting sigmas everywhere. It depends on there. So loss depends upon, loss is a function of AI minus the final actual output, right? Square. AI depends upon sigma of Zi. Zi depends upon, up to a bias term, it depends upon Wij and activation of the previous layer, this activation, right? Now, this activation will, in the same way, will depend upon activations of the previous layer. And so what happens is that if you want to find this, what you have to know is IJL. For every possible value of L, you want to find all the gradients. And how we do that depends upon, so there's a systematic way to keep on, first you find the gradient here, use that, you find this, AJ, AI, and you use this AI in the layer L, and you use this to compute WL, WAJ in the layer L minus 1, and you keep on moving back. But because you can compute this, you'll be able to compute these things. And there's a little bit of a mathematics. So what happens is something quite interesting. In the forward pass, you just do matrix multiplication, and activations. You come up with the output. The output is wrong. You compute the loss, and then you find the gradients in this layer. Then you back propagate, use that value to create the gradients here. And then you back propagate and you use that to find gradients in this layer till you're done, till you have exhausted the layer. So it is like forward is just the compute, network compute X. Backward is gradient, back prop, and that's why it's called back propagation. Gradient gets propagated. The gradients get propagated. Are we together? Gradient with respect to the activations get propagated back. And it is nothing but the simple situation. It is the chain rule. And while complicated as it looks, there is not much more mystery to it. The only thing is when you're doing the calculus or writing the formula down exactly, you have to be a little careful of the subscripts. Now, which node is being activated, which weight are you looking at, and so on and so forth. So you have to keep track of the subscripts. Other than that, there is no magic to it. That is all that there is to it, right? Next time we'll do it a bit more carefully and do this, finish the back prop. But for today, this is hopefully what we say. And this becomes very simple if you look at a very simple situation. So suppose you have only 2 neurons. This is input and single input. So you have a weight W1 of neuron 1, W2 of neuron 2, right? Bias B1, B2. Let's think about this. This produces, what does it produce? This neuron will produce an activation A1.
Correct.
This will produce an activation A2. Right? Now let's work out. Loss is a function of A2 minus Y square. A2 is a function of activation of B2 plus W2 A1. The input to this is A1, the activation of the previous neuron. And what is this, which is the same as Z, right? So you can say A2 is the sigmoid of Z2, this thing here. Z2 is, of course, by definition, W2A1. And now what about this guy? Z2 is done. Now, what is activation? A1. A1 still needs to be found out. It turns out A1 is the activation of Z1, this thing here, where Z1 is equal to B1 plus X times W1, right? So X being the input. So you see how if I make this W, what does this respond to? It responds to changes in this, 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 this. But the way it works is, if you look at the last layer, A2, first of all, let's compute Z2. Z2, it is made up of bias B2, activation A1, and weight W2. Do you see this by formula? Just by this. These three elements go into this. Does this make sense, guys? And from Z2, you can compute the activation 2. From activation 2 and the actual data value, you can compute the loss is equal to A2 minus Y square. Isn't it? So a loss depends on A2, A2 depends on Z2, Z2 depends upon B2, A1, W2. But what does, these are things, these are parameters you can control. But what about this guy? This guy again depends upon Z1. And what does Z1 depend upon? It depends upon B1, right? Now the input for this is fortunately just X, right? And this is W1. You see how it goes back. And suppose this was not this. Suppose there were many, many layers. The same picture now, let me make it lots and lots and lots and lots of layers, right? So what will happen is this would not be the X, it would instead be the layer even before that, right? So suppose I'm looking at this layer. Now make a small picture. Z of layer L produces activation of layer L, the final layer, which produces along with Y, produces the loss function is equal to AL minus Y square. But ZL comes from BL, AL minus 1, and WLs, the weights in this particular layer, they produce this, right? But this comes from, again, a tower of things, the same tower. It comes from ZL minus 1, right? ZL minus 1 comes from BL minus 1, AL minus 2, WL minus 1. And so you can keep going back. And that process is the backprop. When you do this, when you do the gradients, because you have to compute the gradients, like little change in this is affected by this, by this, by this, you ultimately realize that all the W's and the weights, they wiggle and they contribute to this. You have to shake them a little bit if you want to get your loss right. And so this is your backprop journey. Journey for gradient. This is it, guys. This is backpropagation. This backpropagation, today we know, was discovered many times actually, and it has its roots going back to 1950s and 60s, when computers were just emerging and there were vacuum tubes. The real significance of this was realized by, amongst other people, Hinton and a few other scientists, computer scientists, I believe around 1979, 1980. is when the real value of backpropagation was discovered. And so it has been used, it has been a workhorse of the neural networks for a very long time. Right? So this is the important topic of backpropagation. We can carefully do the math, but we are practically there. We can work out the indices and do it a bit more carefully and so on and so forth. Or we may not. We can just skip it and move on, depending upon it. Now, it turns out that I deliberately followed the convention of a certain video. Because this, by the way, when it is explained in books, unless you're very good at calculus, you don't see it. If you're good at calculus, you see it immediately. But if you're not, it looks like a bit of a struggle. So there are two lovely videos, 3 blue, 1 brown, 3 blue, 1 brown. These are people who make beautiful visualizations of the mathematics. It's a delight to watch their videos. So they have created 2 videos on backpropagation. And I've deliberately kept my convention aligned with them, right? So do watch those 2 YouTube videos. Kyle, could you please add it to our class resource?
It's already there.
It's already there. Very good. So guys, as a review, please do watch those videos. Watch those videos and also go take quiz 1. You're ready to take quiz 1. Many of you have not taken quiz 1. Go take quiz 1. Even if you're reviewing this course, go take that quiz and you'll benefit from it. Right? 2 videos. Follow through that. Now, the main textbook that I gave, that is there on the course portal, there the backprop is a little bit harder to understand because it uses the full glory of matrix mathematics, right? So you may get a little bit lost with all the symbolisms and all these indices and matrices flying around and transposes of matrices and so forth. So I would say it doesn't add anything new to understanding backprop. It adds the mechanics of the computation with the mathematical details. But the intuition is exactly the same as what you get using a much simpler notation. So review backprop now, and we may either continue on or we may get into the, you know what, let's do one thing, the mathematical details of backprop, let me make it as an extra session, because it is nothing but repeating the same thing, but being very careful with the indices and the layers for the W's and the A's, and that's all it is. I'll do it in a separate session so that those of you who are interested can attend it. Those of you who are not can sort of skip it and stay at this level of understanding. Right? But this is how neural networks work, guys. You need to update all the weights. To update all the weights, you need to take the gradients with respect to the activations. Layer by layer, you need to backpropagate that. Right? And when you backpropagate, you are able to find the gradients of the weights in the previous layer and the layer before that and so forth. So a wave of backpropagation takes place in which all the gradients get evaluated layer by layer. Right? That is backpropagation, a very, very important method, right? The workhorse of the neural network. It's what makes the neural networks work or learn, but that is it. Any questions?
So to begin the backpropagation process, are you changing the weights of just one of the output neurons?
No.
Or all of them?
No, all of them. So what happens is that, so suppose you have a big neural network, right, with layers after layers after layers. Input goes in, and if you think of this entire thing as a function G, what will come out is the final layers activation, but essentially a Y hat will come out, right? Now this prediction you can compare to the reality Y to create a loss, which is a function of Y hat Y. Right? Whatever function is, here I took Y hat minus Y square, some squared error loss, but whatever function it is, doesn't matter. When I can compute the loss, now I can compute the gradient of the loss with respect to the activation of the last layer, right? And from there, what I really need is somewhere in there are lots of these weights sitting there at some layer L. What I really want is this, and backprop gives me a way to compute all of them. Ultimately, what we want to do is compute this guy with respect to weight, which is this giant thing, W, every single possible value of these W's and L's, I, J, L, because that's all the weights in the system, and the biases, include the biases. But once this is computed, the rest is easy, because W, I, J, L. So first next stage is compute the gradients. Once the gradients are computed, the next thing is just to take the learning step, which is because this is the only thing that you need to know to be able to take a step of learning or wiggle the weights a little bit to improve the loss. Right. So the steps are forward step, forward 2, compute loss, forward will compute y hat, compute loss, 3, compute back prop, and compute gradients, 4, like learning step. That is it. Learning step, that is gradient descent. The learning step is of gradient descent. That is it.
Okay, yeah, so it's just one whole congruent process. That's why all the weights and all neurons are being changed. Okay.
That is it. And that is it. And that is all there is to this. And now the PyTorch, when we use the PyTorch framework in this course, you will see that this is very elegantly done. So suppose your network is called network, right? A network function is there. You give it X to produce Y hat. Code will look like this. Then you would compute loss is equal to whatever loss function it is, loss function, that is LF. Let me just, and I'll represent it as L, Y hat, Y, label. This is the label value, the actual label, what it should have been. Then you compute the gradient. And then you do the step. Literally, the method is called step, right? And it's called backward. I think the specific method is just called backward. Backward will compute the gradients, right? Actually, let me write it this way. Backward computes the gradients, and then step learns. That's it. Four lines of inner code. That is the inner step in the neural network training. And we will walk through the code on Wednesday, and you'll have fun with it. Once you understand this backprop theory and everything, you will see that the code is literally these few lines in training a neural network. And it's quite straightforward code. All right, guys. So with those words, it's only 10 minutes to 10. I'll leave the last 10 minutes for questions. Any questions?
Asif?
Sorry, 1 second. Kate, you have a question?
Why is label data?
Why is the label data? It's the actual reality, the ground truth. People often use the word the ground truth, the label, the actual value, so forth. Kyle, go ahead.
Yes, so it would be best if people learn about the autograd feature of PyTorch.
Yeah, that is in the lab.
Okay.
In the lab part, yeah, we'll do that.
Okay.
Next time, autograd is what we will learn.
All right. So, and if you can scroll up the part where you wrote this inner loop in detail, I just have one question.
The inner loop, where is the inner loop? Yeah, this inner loop.
I still can't see it.
You can't see that?
Ah, yes, it's finally scrolled up. So the backward pass should be the third point, right? And the fourth one
Yeah,
should be the
this is the back. This
optimization.
compute gradient is called backward, and a fourth is called the step. Right?
Okay. Okay.
How you do? Oh, sorry. Actually, the word here, backward learning step, backward pass. No, this is the backward pass. This is right. Backward pass, and this is the learning step.
This is where we use the optimizer.
Yes, the optimizer we use right here because see here, you use the optimizer to compute the loss.
Okay.
Right? So mean squared error loss or cross entropy loss and so on and so forth. So once you compute the loss, the optimizer is the atom. Like, yeah, your atom is used here. Your optimizer comes here because this is the optimization step. Step number 4. Let me just call it optimization is step number 4.
Okay.
Is that clear, Kyle? Was today's session clear to you?
Yes.
Any other questions, guys? Is this all clear or was it like information overload today? Anyone? Any feedback? This is about as hard as it gets, guys. After this, we'll have a pretty smooth sailing for some time.
It's good, Tasha. Yeah, maybe once we repeat it a little bit summary, then it makes sense. Yeah.
Yeah, and we'll iterate over it.
Yeah, right.
Yeah. All right, guys, if there's no other question, then I will end. Then I will end for today.